So good afternoon, everyone. Welcome to this session on discourse. I think what we're going to see from the 3 full papers that we have are some fun, or some very new techniques for taking approaches from network analysis and approaches from natural language processing to really do some very new and sort of novel work as people are looking at learning data. So with that, I'll introduce Ulrich Hoppe with his presentation.
Thank you very much, Marcelo. Good afternoon. So I hope you're enjoying the conference as I do. So I'm going to tell you something about analyzing the flow of ideas, the evolution of knowledge, and also something about profiling contributors based on that analysis in an open learning community. I am a computer scientist from the University of Duisburg-Essen, indeed not far from here. If there are cross-border regions, and in Europe we believe there are, we could say it's still more or less the same region that I'm from. And my co-authors, Tobias, Tilman, Göhnert, they are working with me, also computer scientists. And Iassen, Halatchliyski, the first author, who is currently on a trip to South America, so he couldn't give this presentation himself. He's originally a business administrator and is now completing his PhD in psychology at the Knowledge Media Research Center in Tübingen, in conjunction with the University of Tübingen. So we are kind of an interdisciplinary group. I should use this. And so first, the agenda. I mean, if you remember this, if somebody asks you what was this about, you just should refer to this page. I think it's almost everything is there that you should know. The problem. So the problem that we deal with is to characterize the evolution of knowledge in knowledge-creating communities, a bit broader than just learning communities, but applies to many learning communities for sure. The approach is a specific one that we have taken from the field of scientometrics. I will say more about that. It is called main path analysis, but to be able to apply this more or less well-known method, at least in that field, we had to make some modifications. We have an example case, which is Wikiversity, using Wikiversity data. And I will say a bit about the technological development, the technical development. Namely, this is embedded into an analytics workbench, which does more than that, but also this. And I will conclude with telling a bit about our zone of proximal development in this research. So, to remind you, this is not an empirical paper. It's not that I have studied specific things with Wikiversity in first place. We have a method. It's the development of a computational method, and this example is to show us what kind of insights we can expect from this method. This is the function of the example, as I would tell you. Okay, the background we have done on the 2 sides. We have done studies of productive collaboration. For instance, in my group, we have studied productive online communities, as we call them, namely and especially open source software developers. The interesting thing is you have the whole traces of these activities open on the net. There are no restrictions. For instance, in social networks, it's often very difficult to get to these data. Here, it's all open, and it needs to be open because for the newcomers, it needs to be all there. So this is a very interesting field, also because of the accessibility of the data. Iassen, Halatchliyski, and Ulrich, the professor of psychology in Tübingen, they have also studied collaborative knowledge construction, using, for instance, Wikipedia. Ulrich has what she calls a co-evolution model of learning between individual and collaborative learning. And there is another piece of background, which is an ongoing EU project, indeed not Intel. Most of us doing EU projects are usually in the area of technology-enhanced learning. This is in Science in Society, another program. So it's about science analytics or scientometrics, or want to go a bit beyond the classical scientometrics and consider more social impacts of science. And of course, there are, as already said in the introduction, there are various network analysis techniques behind that we have used. So the conceptual background now for the questions that we want to answer is, in first place, knowledge building. Knowledge building is the creation of what we would call epistemic artifacts that are shared in a community. This has been very much elaborated on by, for instance, by Skardamalia and Bereiter. Here is just, most of you will know that, but just to remind you, the basic thing here is the analogy of knowledge building in learning to doing science. I mean, the modality of learning here is the same modality that you have in science. And this is the main argument for us to look more deeply into methods to analyze the scientific production and transfer these to the knowledge building in the learning area. So we want to reuse science analytics, or better known as scientometrics, to analyze knowledge building, to characterize the knowledge evolution in a community. So some more conceptualization. This is a bit broader. This picture is a bit broader than the things that I'm particularly going to study. The picture that you have, the entities that you deal with typically are actors and artifacts. The basic networks that you have are what the network analysts call two-mode networks. So one modality, one entity type are the actors, the other entity type is the artifacts. And in first place, you have a relation you call it create or author, which establishes primary links only between the actors and the artifacts. So it's what in graph theory you call a bipartite graph. But there are induced relationships. For instance, there is an induced relationship between the documents or the artifacts A and B here. How is it induced? It's induced by the authorship of P for both. So you can induce such relationships also between the actors, of course. These are the co-authors of a paper. This gives you a triangle. The co-author subnetworks are always cliques, what we call in graph theory cliques. So this is the typical situation that you may, of course, have direct communications. Often this is not modeled, at least not in scientometrics. So what scientometrics deals with is typically the authorship relation, co-authorship networks, and of course references, citation networks. This is where we are, where we start from. So now main path analysis. The guiding question for main path analysis, if we have a graph of the dependencies between such knowledge items, between such epistemic artifacts, how can we identify the main pathways through which supposedly the knowledge evolved? It's about a heuristic approach. It's not even there in the field of scientometrics. There's still another question, is the validation. If this heuristic is really corresponds, for instance, to human judgment. But it has been used, and you will see that it may give interesting insight. So we use the citation links here as a basis. And the interesting thing about citation links in publications is that the citation graph is usually acyclic. How come? The references always go back in time. You can have, in very rare situations, you can have papers, for instance, appearing in an edited book, cross-referencing each other. Then you have to clean up the data for that. But you need, for the method, you will see, you need that the graph does not have cycles. Okay, the first historical example of this method, application of this method by Hamann and Dorian, was in 1989, and they used a set of publications on DNA, so a historic set of publications on DNA. And these publications, you see, these are the older ones, these are the newer ones, something you have to think about first. You see how they are interconnected by citations. Indeed, the links that you see here cannot be the citation links, they are the inverse citation links, because the knowledge flow would, of course, go inverse to the citation. That's the idea. The information flows from the old paper into the new paper. So, and here indeed you see this main path. Main path means this is the assumed main line of evolution of knowledge in this field. Okay. So what are the formal properties? We have citation networks as directed acyclic graphs. There is this implicit notion of time that the links are inherently loaded with time. If you have the inverse citation relation, you go from the older to the newer. So you have sources in such a network and you have sinks. The sources are those that do not have predecessors and the sinks are those that do not have successors. What you can do now, and that's the basis for one type of algorithm for main path analysis, that you add one virtual source before all the other source links and one virtual sink after all the other sink links. You see that here. So you see here, that's a virtual source. That's not really a node that was there, not really a publication. This one, the same. This allows you now to do the following exercise, and this is indeed the way how Batagel, a person quite well known in network analysis from Slovenia, he suggested this method to calculate the main path. Given you have this one source and this one sink, you can now draw all trajectories from the source, the one source to the one sink. This will give each edge a count. The count says how often has this edge been passed on any one of these paths. For instance, this one was 4 times, this one was just twice. Now, you select the path with the highest edge weights. This leads to the following here. You see, of course, first you select this one, 4, you go with a 3, and then here you have a bifurcation because you have an ambiguity. You have a 1 here and a 1 here, so you cannot resolve that. So even these so-called paths, they may be multi-threaded. And of course, you would later on cut off the artificial sink and the artificial source again, so you may even have a disconnected set of such paths because you are not really interested in these artificial nodes here. But this is the way how it is calculated. Now, we go to the example. The example is, as I said, Wikiversity. This is the self-description taken from the self-description of Wikiversity. They claim to be a learning community, very broad in range, also over different levels of education, and involving both producers and consumers in this community. So this, what we see here, is the category tree starting here with philosophy. And indeed, philosophy and medicine have been our 2 main examples to look into more deeply. Here, this is a cut from philosophy. I can get rid of Adam. Oops. So I just wanted to get rid of Adam, not caught. Oh, now. Yes, that's the. I should have deleted this Fujitsu software already. Okay. Anyway, so philosophy on the whole has 228 pages, and here you see these names are author names as they appear on Wikiversity, so it's not really secret data. And here you see the pages. For each of the pages, you have an evolution, the versions, and you have the authorship of the versions. And here, for instance, if you look at that, there K.Y. Park introduced a new page on logic and linked it to the page Hegel and the wisdom page on creation. So this is more or less what this diagram tells you. Now, this situation is no longer the same as in publication, and this is a complication. This has to do with time and the acyclic property of the networks. Here, these networks are no longer acyclic. Typically, web pages cross-reference each other in both directions. This can happen. So the resulting graph is not a directed acyclic graph, and we can no longer assume that there is this implicit notion of time in the links. So what have we done? We have introduced for every change, as already could be seen in the conceptual diagram, for each new version of a page, we introduce a new node. Even when the only operation is to link this page to another page, then we would also count that as a new version. This gives us now, indeed, a directed acyclic graph again. There are some redundancies. For instance, if this is, by the way, users, just users as numbers, there was one new version here, and this operation here was a linking of, this was, here this page 2 was linked to page B, because we count always the information flow. So this is the inverse citation relation. Of course, this stays. Once it is established, it stays. We could repeat it, but we don't do that. So if there is a problem in the model, if links are deleted, we would have to do something. But so far, we haven't seen that in our samples. So we don't deal with deletion of links here. We just accumulate the links. And then, so we leave out the redundant links, which gives us this simplified graph, which is directed acyclic, so we can run now main path analysis on it. And this is how it looks like. For instance, with the medicine example, medicine is sufficiently rich, so we have used it as an example. Here you see two different types of application of the method. One has a minimal branching. Only where the ambiguities force us to do so, we do a branching. And the other method, sometimes you want some branching, you want a richer threading, then you allow for some margin. So if one branch has only 3 and the other has 4, you may still take the 2. So you may have different structures resulting here. Here you can see them in a bit more detail. Here you see that this author, 15539, was quite active in adding new versions and also linking, in interlinking the existing pages. Now this is the version with higher branching. You see other nodes coming in. It's not another cut of the network, not another perspective of the network. What you really see here is that there are now other main paths, because now you have more, you allow for more paths to be admitted in your, this is not the whole network. This is always only the main path filtered network. Okay. So what do we have at this point? What insights do we gain from this knowledge flow analysis? Our point is, our claim is that you get a better understanding of the contributions in context. And to show that, I want to give you an example that has to do with user or author profiling. Look at this table, and maybe look first just at these 3 numbers. You can also consider the 98, referring to user 385. So the 3 here appear to be more or less equal in productivity. There's not a big difference in productivity. So here you couldn't distinguish them. And my point is now that the method gives you interesting indicators for distinction of these 3 people. Look at this now. You consider behind the slash there are not just the contributions, but the number of contributions that are on a thread of the main path. We always say the main path, but you have seen that the main path itself can be threaded. And so this gives you a distinction at least between now the first 2 and the third one. The third one has considerably less of his contributions on a main path. Now, go further than that. Consider, this is the references received, so the incoming citations, you are cited, you are referred to, and this is the references established. And here you see, indeed, also a big difference, particularly in this column, between the first and the second one. And how could you interpret that difference? We said you could call the first one a connector. The first one doesn't receive a lot of highly relevant references, although he has created quite a number of references. He has also received some, but only one was on a main path. So, whereas this person, number 2, is, I mean, in social networks, you could say this has to do with prestige. Evidently, this person is more important for others. There is a caveat, though. There may be self-citations. On the other hand, we can say that even though there were self-citations, and by the way, we have seen this guy. You remember maybe from one of the diagrams, and he did a lot of cross-linking. 2 pages that he was involved in, but he was successful. These were on the main path. Now you can say, okay, then he has created his main path. Oh, now you have to see the whole production and the whole picture. If the pages, in relation to the others, were relevant, I mean, that's something. So, and you see that the third one here, the yellow one, you could call him a worker, productive, but hasn't done very many relevant things. So, this is what we can do with the method. Where are we now? In 20 minutes. Oh, thank you. That's perfect. So, the technology behind this is a workbench that we have created in this project SysOp. It has been used for many different purposes, and we call them workflows. The visual representation, and so the GUI of this workbench, is based on a pipes and filters approach. You may know that, for instance, from Yahoo Pipes. But this is just the GUI. The content of the filters are agents. And these agents can be defined in our architecture in different languages. We started with filters in Java, in Prolog. We have also used Python. For instance, for natural language processing, Python can be quite interesting. But currently, most of the network filters that we use are more or less uniformly implemented in R, in the statistical language R. So we have a wrapper for R, so we can plug in our R scripts into the workbench. And behind that, supporting the data flow, it's a data flow approach, of course, we have a cascaded processing model that is supported by a so-called tuple space architecture. And it's all behind a web-based interface. You can access it through the web. We have done some exercises with a number of users at a time. Still, from time to time, we run into trouble. Some have seen that in the tutorial on Tuesday. But we are working on it, and it's more and more usable. So this is how it looks like. Maybe I should explain a bit the colors. These are filters. Usually you start with a data upload filter. Then often you have a format transformation because your original data are not in the format that your later processing unit requires or assumes. So here, for instance, we transform from GML format into our SysOp format that is suited for all the R-based calculations. And then we have our main path analysis implemented in R. And then we have so this is for decoration to get some additional information on the graph. And then finally, we have a visual output that would look. So here you see it has run through. If the run is complete, you get a result page, and then you click on the page and you see the results. This is now not a swim lane diagram. This is the complete graph, the complete medicine, Wikiversity medicine graph that we have used with the main path in color orange. So you see the main path embedded into the original graph. Another visualization, but honestly speaking, we do not have the swim lanes yet in our workbench, so we're just working on that. But that's the detail. So where are we and where are we going? Where are we heading for? So our zone of proximal development. So we have this method, main path analysis, specified for our purposes. I think you understood there were some modifications needed. The original idea really goes back to Iassen, but I think it was necessary to have some computer scientists to really formally specify that well. And we can use it now on the workbench. There are some technical issues that we are dealing with. There's one problem that I haven't mentioned yet. The question is, on which data set do you try to derive main paths? For instance, we have taken the whole CSCL publications over years, or the whole AIED publications over years, or you can throw them together. What do you expect? There will not be one main path. There will be kind of thematic subnetworks. So if you want to find these, you need a specific seed, as we say. So you can start from the end nodes, calculate a backwards fan, and then go again from the old to the newer ones. Then you have the chance to get a more, say, coherent picture. That's a problem, and we are working on that. Then the other thing has to do with, say, extending the range of the method. For instance, we are now in a master thesis, a very good student of ours, is applying this to chat data. In first place, he has replicated Dan Souther's contingency and uptake analysis, also using the same data, the tapped-in data, now he has added to that main path analysis. That would conceptually help you to understand where in these chat conversations were the main threads of information flow. We have to validate that. This is not about validation, of course, yet, but we will have another thesis that we are just establishing with a psychology colleague of mine, Daniel Bodemer. He was in Tübingen before. He's going to try to validate that on a chat data set that he has also analyzed before. So we can see what our method brings, what he could also see, or what could be different. And we are also blending this method with other methods in network analysis. For instance, there is the so-called link prediction approach that's quite specific to scientometrics. In scientometrics, one of the basic tasks is you want to predict future co-authorship. Yeah? Or we have also extended it, that was Tobias Hacking's master thesis, to predicting future topics for certain authors. And we believe that we could use main path analysis in the conditions, say, to further elaborate certain conditions for later predictions. Also, you have seen that you can interpret what the figures, when you, say, add the main path weight to your figures, like in production, that can help you to profile the productivity. So it could be used for defining roles as role indicators. We know role indicators from social network analysis, like brokerage, broker roles, mediator roles. Often you look at betweener centrality, for instance. We think that these indicators could also combine with social network analysis. So this, by the way, is the current version of the workbench for the chat analysis. This is just a screenshot from the student's work. Here in this part, you see the specific input window to parameterize the chat contingency analysis and uptake analysis. So this is the replica of Dan's work. Then you get a chat page rank graph. And here you add on now the main path analysis, which gives you this, what you see here. The breadth of the links now indicates that these utterances were supposedly on a main path. Again, still to be validated, but we can calculate it, whatever. So, okay, the credits. Iassen indeed discovered main path analysis and brought it to us, and hopefully so to learning analytics. Tilman Göhnert is the principal implementer of the workbench, and Tobias Hacking has hacked the algorithms that we have used to a large extent. And so I have just represented this piece of work, and maybe I've also done something for the synergy here. Thanks for your attention, and I think we have time.
Yeah, we have a few minutes for questions.
Okay, perfect.
Thanks for a really interesting presentation, some really innovative work. I have just one question and one thing I'm not quite sure of. in both examples, the citation example and the Wiki University example, are connectors, they're much more likely to be interdisciplinary folks, aren't they? I'm trying to think in here in the medicine example and in this one, that I wonder if among the if viewing this as kind of the earlier example of citations, it seems like connectors are more likely to be interdisciplinary folks. Is that correct?
It depends a bit on your data set, I would say. I mean, if you look here, that's gynecology. Essentially, this is about diabetes. So if we talk about interdisciplinarity, it would be within the medical field.
Right.
Yeah, so,
yeah.
Of course, if you have a broader data set, and if you look, here you could say, but interlinking certainly means just not elaborating on one idea, taking into account other ideas. How broad the range of ideas is, this may really vary. So here you see really the example. Of course, it's very much inside the medical, the medical taxonomy.
The other thing is when you talked about working backwards, okay, and I'm probably wrong in this, but working backwards, it strikes me as you'd be more likely to miss out on some small paths that die out quickly, that go nowhere. I mean, it strikes me that you work backwards, then you could also work forwards to make sure that you didn't miss out on any of these small paths way off the main path that went nowhere.
Yeah, usually you would do both. I mean, this working backwards was, I mean, there is this pre-selection problem. If you do not pre-select, you get these not very coherent, possibly many pathways. We have done that, as I said, with CSCL data. I have the AI data, for instance, AI in education. It falls apart into very different pathways. Each pathway, again, such a graph, but much smaller, narrower, of course. And if you want to avoid that, if you want to ask more focused questions, then you need the pre-selection. And that's the seeding thing. Mm-hmm. So you set a seed, and you can set a seed from the end, or you can set a seed from the beginning. That was this working backwards or forwards.
Let's thank our speaker. So next up we have Simon Knight from the Knowledge Media Institute presenting.